Hello everyone, my name is Gilbert and currently I am PhD student from Department of Chemistry of Chung-Der Christian University in Taiwan, and I'm supervised by Professor Xiao. And in this video, I would like to briefly introduce you about my paper with the title is Comparisons of the Chronic Toxicities of Graphene and Graphene Oxide toward adult zebrafish by using biochemicals and phenomic approaches. So first, let me introduce you a little bit about the graphene and graphene oxide. Graphene, a single-layered hexagonal lattice composed of carbon atoms, is the simplest form of the carbon layer and the thinnest material produced up to now. With a typical thickness of 0.32 nanometers, a single or few-layered graphene can be obtained from high-purity graphite using either a chemical or a mechanical approach. Meanwhile, graphene oxide, another two-dimensional carbon material, is known as the oxidized form of graphene, with a carbon layer decorated by oxygen functional groups as a result of oxidations and chemical exfoliations of layer crystalline graphene. Although graphene oxide is similar to graphene, its properties are very different from that of graphene. Graphene oxide nanosheets are hydrophilic in nature due to the presence of the oxygen functional groups. Thus, due to its hydrophilicity, graphene oxide is easily dispersed in water. Meanwhile, graphene possesses a hydrophobic conjugated carbon network that makes it easy to be modified by various kinds of functional molecules and nanostructures. Since it was discovered in 2004, scientists have engaged in research of graphene and its derivatives because of their distinct physicochemical properties. The unique structures allow it to have many unusual and attractive properties, including large surface area, an unusual quantum Hall effect, superior intrinsic electron mobility, and exceptional thermal conductivity. These excellent properties make graphene and graphene derivatives versatile materials in a broad range of areas, including separations of environmental pollutions, non-volatile memory devices, energy storage devices, optical instruments, and sensor catalysis and surfactant. However, so far as the nanomedicine applications are concerned, graphene and graphene oxide potential toxicity has received relatively little attention, while toxicity is an important issue that must be addressed to regulate their usage related to living matters. Even though graphene and graphene oxide toxicities have been addressed in some prior studies, little is still known about their effects on adult zebrafish behavior. Moreover, most of the studies in adult zebrafish or more sentient animals use only relatively higher concentrations than the predicted environmental concentrations. So, the aims of the study is 1. To compare graphene and graphene oxide's potential adverse effect at predicted environmental relevant concentrations in adult zebrafish behavior. So, why this behavior measurement is important? Because since nowadays, behavioral assessment has emerged as a crucial tool to inspect toxicology of materials. In fact, a prior study showed that neurobehavioral study gave more relevant and reliable results aside from its less cost, robustness, and effectiveness for toxicology research. The second, we want to conduct biochemical assays to help in elucidating the possible mechanisms that underlie their behavior toxicity. Also, to further examine their effect under different concentrations, 2 doses of graphene and graphene oxides were studied. This is the outline of our study. First, we do the physical properties characterizations of the graphene-based nanomaterials by using some characterization techniques, including Raman spectroscopy, X-ray diffractions, transmission electron microscopy, atomic force microscopy, and ultraviolet visible spectroscopy. After that, we incubate the zebrafish with the graphene and graphene oxides, and after 14 days, we conduct the behavioral assays, including novel tank assay, neuropathic assay, predator avoidance assay, social interaction assay, and Shoaling assay. After that, we dissect the brains of the three zebrafish and conduct the biochemical assay, which checks some biomarkers in the brain, including serotonin, kisspeptin, dopamine, cortisol, acetylcholine, acetylcholine esterase, oxytocin, and ROS. Before I started to explain the results, I want to tell you that not all of the behavior endpoints are described in here. I just show you the most representative behavior endpoints to describe the result. If you are interested and want to know more, please feel free to access the manuscript directly. In order to acquire the unique bulk and surface structure of the graphene-based materials, some characterization techniques were used in the study. First, from the X-ray diffraction spectrum comparisons between graphene and graphene oxides, we found that the D-spacing value in graphene oxide was efficiently higher than that in graphene, which is it accounted for the uptake of oxygen-containing functional groups and water molecules between the hydrophilic interlayer basal planes of graphene oxides. Next, by the Raman spectroscopy, we found that the positions of G and D bands of the graphene oxide band are almost identical to those of graphene. These experimental results demonstrate that the existence of a higher defect in the graphene sample. So next, by UV visible spectrum between graphene and graphene oxide nanoparticle solutions, we found a characteristic absorption speed at around 230 nanometers in these two solutions was shifted to longer wavelengths, which is 290 for graphene oxides and 305 for graphene, suggesting an extended p-stacking interlayer conjugations. Furthermore, we also checked the size distributions and transmissions electron microscope images of graphene and graphene oxide nanoparticles. And later we found that a bigger mean particle size of graphene in comparison with the graphene oxide. Furthermore, in the case of zeta potentials, we found that the mean zeta values of the graphene and graphene oxides are 96.5 and 84.4 millivolt, which suggesting the high stability of both dispersions. In addition, to perform the horizontal dimensions observations, atomic force microscope is regarded as a convenient approach for thickness measurements and layer number counting. By using AFM, we found that graphene sheet thickness in the graphene sample was found to be mainly in the size range of 0.4 up to 1.1 nanometer, while single layer of graphene oxide is generally about 0.7 up to 1 nanometer. So let's continue to the behavior test results. First is the Novelty Test result. The Novelty Test is a method to observe zebrafish locomotor activity and spatial exploration's ability to respond to a novel environment. Here, to observe the changes in their locomotion's activity, several behavior endpoints, namely average speed, freezing, swimming, and rapid movement time ratios were measured. Meanwhile, to assess the exploratory behavior changes, time in top durations, number of entries to the top, latency to enter the top, total distance traveled in the top, and thigmotaxis were calculated. After graphene and graphene oxide exposure, we found that low concentrations of graphene oxides significantly decreased zebrafish locomotor activity. Meanwhile, graphene in both low and high concentrations significantly decreased zebrafish locomotor activity. This phenomenon was indicated by significantly low levels of average speed and rapid movement ratio. Furthermore, regarding the exploratory behavior, both graphene groups cause an altered exploratory behavior shown by a significantly low thigmotaxis level. Next, we continue to the aggressiveness test, or we call it mirror fighting test. A mirror fighting test was conducted to assess zebrafish aggressiveness after 2 weeks of waterborne graphene and graphene oxide exposure. Generally, zebrafish bites the mirrors when it sees its reflections. This phenomenon also indicates social motivations or its intentions to communicate with a social partner. From the result, no significant alterations in the aggressiveness level was found in either graphene or graphene oxide treated fish. This phenomenon is indicated by the similar level of mirror biting time percentage. Meanwhile, different results were obtained from the predator avoidance test. Typically, fish shows high anxiety or even freezing behavior as their innate response when facing their natural predators. Predator avoidance tests show that zebrafish chronically treated with both graphene and graphite oxide possess less predator avoidance behavior. These alterations indicated by a significantly elevated level of approaching predator time, as shown in the video. Next, since zebrafish is a highly social animal, concentric interactions as one of zebrafish social natures was assessed by performing social interaction tests. The results show that there was no significant alterations between control and treated groups regarding their social interactions. This phenomenon was supported by no significant changes found in all graphene and graphene oxide treated groups compared to the control. Later on, another social-related assay in form of the Scholling test was also conducted to further support the results regarding the effect of these materials in zebrafish social behaviors. As an innate behavior to avoid predators and reduce anxiety, it reflects the complex interactions of species swimming together coordinately. In line with the social interaction test, normal shoaling behavior was displayed by all treated fish, indicated by the same level of all behavioral endpoints. These endpoints include average interface distance, which shown in the video. Later on, to help elucidate the behavioral alterations observed in previous behavioral tests, the effects of chronic exposure to graphene and graphite oxide on selected neurotransmitter, on antioxidant activity, and oxidative stress in zebrafish brains were investigated. First, we measured the neurotransmitter levels and found several neurotransmitters which are serotonins, acetylcholine, and dopamines, and also cortisol were significantly decreased in brain tissues in 0.5 ppm graphene exposed fish. On the other hand, intriguing results were found during reactive oxygen species or ROS measurements. From the results, a significantly high level of ROS was displayed in both 0.1 ppm graphene and 1 ppm graphene oxide treated groups. Next, to investigate the difference in terms of behavioral alterations patterns between graphene and graphene oxide, a phenomic approach was used. Thus, carbon-16 nanoparticles, carbon-17 nanoparticles, carbon-coated magnetic nanoparticles, and magnetic nanoparticles behavior toxicity data from previous publications were included to perform the heat map, hierarchical clusterings, and PCA comparisons. PCA is one of the mathematical methods that linearly reduce the complexity and dimensions of data. Meanwhile, hierarchical clustering is an algorithm that compares both rows and shows that similar rows and similar columns were clustered by the dendrogram, which represents their similarity. Based on the phenomic results, we found that both graphene and graphite oxides groups were closely clustered with carbon-coated magnetic nanoparticles treated groups. After further inspection, we found that even though slight alterations in zebrafish behavior were still detected, a surface modifications in magnetic nanoparticles improve its biosafety and biocompatibility. This grouping is possible since graphene and graphite oxide treatment did not trigger significant alterations in zebrafish behavior in the current study, which is somewhat similar to carbon magnetic nanoparticles results. Overall, the present study has several key points. First one, the graphene and graphene oxide treatments caused some behavioral alterations which were observed mostly in their locomotion activity, exploratory behavior, and predator avoidance behavior. Second, abnormal levels of oxidative stress, antioxidant activity, and several neurotransmitters were on display in the brains of the treated fish. Next, graphene in both concentrations were grouped in a different cluster with graphene oxide groups, which indicated that each graphene and graphene oxide has its unique pattern in altering zebrafish behaviors. Last, both of graphene and graphene oxide groups display diverse patterns that distinguish them from other nanoparticles that were studied previously. To conclude, a waterborne Graphene and graphene oxide exposure cause abnormal behaviors in adult zebrafish and induce oxidative stress, antioxidant activity, and neurotransmitter changes in the zebrafish brains. However, less severity of graphene and graphene oxide was observed in terms of zebrafish behavior alterations compared to other nanoparticles, which are carbon-60 nanoparticles, carbon-70 nanoparticles, carbon-coated magnetic nanoparticles, and magnetic nanoparticles. Nevertheless, the graphene and graphene oxide toxicity are still cannot be neglected and should be carefully addressed in the future. That is all for my brief explanation for the paper. Thank you for watching this video. I hope it can give benefit to you. And if you are interested and want to know more about this study, please feel free to access the manuscript which is already available online.